Hello everyone, welcome to Unit 3 on Forces. Today I'm going to be talking about learning Target 1. We just got done with motion and how objects move and describing those motions. Now we're going to learn about the cause of this motion, which is forces. Our first learning target is basically force diagrams. Students, you're going to need to learn how to draw one of these in order to properly explain the forces acting on object. So it's going to be similar that you must draw a model to signify 1, how much force is there, 2, what type of forces are acting on the object, 3, the direction, and 4, is the force unbalanced or balanced, and we'll discuss that here at the end of this learning target. Before we can even start drawing these, we must understand the definition of a force. Simply put, a force is a push or a pull. And that push or pull acts on an object because another object is interacting with the object you're describing. So when we have a force, they generally exist as a result of two objects interacting, and forces always come in pairs, and we'll discuss that more in depth later on. But understand that, simply put, it's a push or a pull right now. There's two main categories of forces, and within those categories there's many different types of forces. The first category is our contact forces, and simply put, these are forces that are occur when two objects are physically contacting each other. So example of these forces would be frictional forces, when two objects are touching each other and slide past one another. That's called a friction. Tensional forces involve forces that have a rope or a hanging object. Normal force is the force of an object being held up by another object. Air resistance, similar to frictional forces, except we're only dealing with the object in air. And then applied forces, that's simply a push or a pull, and we'll discuss these more in depth when we get to drawing force diagrams. The second category of forces are called action at distance forces. To be very, very simple, these are called non-contact forces. So this involves objects that are interacting, but they do not physically touch each other. Examples of non-contact forces. The main one that we're going to talk about is gravitational forces, or gravity. Basically the pull of the earth on an object. And then also there's electrical forces and magnetic forces. We will not touch base on electrical and magnetic. Gravitational forces is probably the only non-contact force we'll look at. Measurement of force. In this unit, you're going to have to measure the quantity of force, how much push or pull is evident in that force diagram. And we measure force in the unit of called newtons. 1 Newton is equal to the force required to give a 1 kilogram mass an acceleration of 1 meter per second. So we can draw this out here. Let's say we have this is 1 mass and it's 1 kilogram here, and it moves this way, and from here this would be 0, and I apologize for the scribbles here, but this would then be 1 meter. If this object moves this far in 1 second of time, that would be equivalent. The amount of force needed to push or pull that object from 0 to 1 meter in 1 second, we call that a Newton. So that pretty much explains how we get that measurement. Now, do you have to know the exact calculation of how to get a Newton? Yes, I'll show you that at the end of this presentation, but understand that's the definition of a Newton. Measurement of the force continued. Basically, a force is what we call a vector quantity, and that quantity basically signifies both magnitude and direction of a force. Magnitude will describe the size or the numerical value in newtons of the force, and then obviously the arrow will point the direction the force is acting in. When we look at measuring forces, we are not really concerned per se about the actual value all the time. You will have to calculate some forces, but you have to understand first before we get that a force can be balanced or unbalanced. A balanced force means that the magnitudes of the forces acting on the object are opposite in direction and also the same power. Okay, so the magnitude is the same, and then, the direction is opposite. So if we look here, the forces on the left here are balanced forces because, one, the table is pushing up on the book, the gravity then is pulling downward on the book. Well, it's the same. The object is not moving. Therefore, the magnitude of forces acting on the book are the same, and the directions of the forces are opposite. Whenever you have a balanced force, the object is at either a constant speed or not moving. In an unbalanced force, we have forces acting on the book here that are not balanced. So what we have here is this book. It says the friction between the table book surfaces exerts a leftward force upon the rightward moving book. So if this book is moving to the right, and we have a table with a pushing up and a gravity force pulling down, and those two are equal in magnitude and opposite in direction, well, the up and down forces are balanced on this object. However, it is moving down to the right, and we said it has a frictional force moving to the left. Well, the frictional force then would be unbalanced because it does not have an opposite force equal in magnitude and opposite in direction on the other side. Therefore, this book would slow down if it was moving to the right because it's an unbalanced force and friction would take over. We're going to talk more about unbalanced forces when we get into learning targets 2, 3, and 4 as well. Force diagrams, well, we want to use force diagrams to model this relative magnitude and direction of all the forces acting on an object. When we draw a force diagram, the size of the arrow in the force diagram reflects the magnitude of the force, how strong that force is. The direction of the arrow shows the direction the force is acting on, and then each force arrow in a diagram is generally labeled with the type of force that is acting upon it. If we look here, we have an example of a force diagram. This box represents the object in which we are discussing. The arrows represent the size and the magnitude of the force. The direction of the arrow indicates which way the force is acting upon, and then as you can see, each force is labeled. Generally, when we draw a force diagram, we draw a dot in replacement of this square here. Force normal, force gravitational, force applied, and force of friction, those are all different forces that we're going to be discussing more in detail as we begin to draw these. But understand, you will have to know what these abbreviations mean and what force we are discussing in class. Here are some practice slides I'll let you show, and if you need to pause the video during the video, you can practice drawing force diagrams, but we're going to get plenty of practice in class. So here's one. Here is another one that we will practice in class. And then here is a third one we will practice in class as well. So if you want to practice these on your own, you're more than welcome to do so. Finally, one of the last few things here before we end the lecture is you need to know how to calculate forces. When you're calculating forces, you need to be aware of three things. Number one, the units. Units become very important. So whenever you do a calculation of force, you need to know how the units work together to get to the ultimate unit of force, which is a Newton. Second thing that you need to be aware of is the gravity calculation. You must be able to calculate gravity that is acting upon an object in the problem, and we'll discuss how to do this properly within a proper force problem. And then finally, balanced versus unbalanced force calculations. We will go into great detail later on about balanced versus unbalanced forces and how those relate to the calculation specific to a force diagram. The big one I want you to be aware about is calculating gravity. Gravity is equal, force of gravity is equal to mass of the object times 9.8 meters per second. This is a quantitative value, and this number, 9.8 meters per second squared, that is a unit of acceleration, and that is the constant acceleration of gravitational force. We'll talk more about that later on. As you can see, here's an example calculation. If you have a mass or object with a mass of 2.8 kilograms, simply put, to calculate gravity, you plug in, you substitute 2.8 kilograms for the mass, you multiply that together, and you get an answer of 27.44 newtons. You'll eventually have to do calculations like these in class. So finally, to review, the definition of force, number one, is a push or pull on an object. To put it in very simple terms, that you need to know that definition. Number two, you need to identify the types of forces. Is it a contact force? Is it a non-contact force? And what do the abbreviations stand for? We'll go over this more in class. Number three, you need to be able to measure and calculate a force. We're going to use the gravity calculation of mass times 9.8 meters per second. That will be our base calculation, and that will help us calculate other forces in a force diagram. And then finally, the main goal is once we start drawing these force diagrams, you need to remember the difference between sideways and vertical forces, and also we're going to be discussing balanced versus unbalanced forces as well. Please complete the quiz. If you have any questions, again, please bring them to class. I'm not a mind reader. The more questions you bring to class, the better off class is going to be. And the more you know, the more you practice, the better you understand this stuff, and the more successful you're going to be. I'll see you guys in class.